So the equation for restoring force, Fs equals negative kd. And just as a reminder here, so the force of the spring is equal to negative k. What am I doing? Force of the spring, Fs is force of the spring. K is spring constant. And d is distance from equilibrium. TJ, we're working on the notes page. Just got it right there for you. Okay. All right, so that's just a reminder of the equation. Nothing new there. When we're talking about equilibrium for a spring, equilibrium is kind of the balance point. The spring stretches to where Fs equals Fg. So where the spring force and the gravity force are the same. Okay, and then lastly, just a little bit about this negative sign. We've mentioned this before, but Fs and D are always opposite directions. So that's all it means. It just means those two things are always in the opposite direction of each other. Okay. Again, we've talked about this briefly, but I want to make sure to reiterate it here because it's easy to forget.
Why wouldn't it be K and then negative D?
Yeah. So the reason why it's not K is because even though the negative sign's here, the negative sign goes with the equation. It doesn't go with K. So K is actually always positive. So since this number is always positive, then either we need to get a negative answer or D needs to be negative to cancel out. So it'll be one or the other. For what it's worth, when we solve the problems, I'm always going to make D negative. I'm just always making D negative. It just makes it simpler, means I don't have to worry about it. Just take it. All right. So let's look at the lab here, and let's talk about what we found with the lab. So when we were talking about this, the first thing we were talking about is spring constant. Okay, and we found in the lab that the spring constant was inversely proportional. That meant that when we increase the spring constant, we decreased the period. Okay, so when we made one thing go up, we made the period go down. TJ, why don't you just put that like on the, you can put it on the floor under your desk, just so your phone's not in front of you, or close it all the way down. It's fine. There you go. Perfect. Okay. All right. So why does spring constant make it inversely proportional? So when you increasing spring constant, or when you change spring constant, so changing spring constant changes the force. But nothing else. So in other words, more spring constant, so more K means it moves in less time. That's why the period goes down. So if you make K larger, then the other thing goes down. And that's why it's inversely proportional. And again, there's more force, but we don't do anything different. Okay, we don't do anything different. It doesn't travel further. It doesn't have more inertia. Like, nothing is different about it other than the fact that it has more force. And so the more force makes it go in less amount of time. The opposite would be true, too. If we decrease the spring constant, have less force, so it go in more time. All right, so that was spring constant. Second one here, mass. So mass, we said, was directly proportional. When we increase the mass, we increase the period. So more mass meant it took longer. Okay? So why would that be? Well, when we change the mass, we increase inertia. So changing mass changes inertia. In the same way. But does not change force. So it does not change anything about the force acting on the object, but it does make it either harder or easier to move. So by making it harder to move, the amount of force you had is not going to be enough to move it the way you did, so it's going to move in a longer period of time. It's going to take longer to move. Likewise, if you have less mass, it's going to be easier to move without making your force any less. So it'll be more force than it needs, and that'll, again, take longer. Okay? All right. Amplitude and displacement, we found that had no effect. All right, and the reason for this one is we know that amplitude and displacement makes it go further. It's got further to travel. So you would think that would take longer because it has further to go. But just like in the spring one, the more you displace it, the more force you give it. Okay, so if you look at my equation d, negative kd, so the larger the force, the larger the distance it is from equilibrium, the larger the force is going to be. So, changing amplitude changes distance traveled. But also changes restoring force to balance it out. Okay, so we got to balance it out, and we do. So that means that the restoring force is going to end up being enough to balance out the larger distance. All right, and then the last one. We didn't test this one in the lab just because it's impossible for us to do this in the lab easily, and that's the acceleration of gravity. While gravity affects pendulums, it does not affect springs.
How would we change gravity if we weren't doing it? Like if we could, how would we change it?
You'd have to go to different places.
Like the moon?
Yeah, or you could go to like higher elevations on Earth. All right, so why does gravity not have an effect? And the reason gravity doesn't have an effect is because it's not weight that affects pendulums, it's mass. So because it's not weight, there's nothing about the, like, changing gravity doesn't change the weight, the force. It just changes kind of how it moves, but it balances out with the inertia. So acceleration due to gravity does not matter because it has no effect on restoring force. So it doesn't change anything. It's actually really weird because it's not like amplitude where like it changes two things but they balance each other out. Like changing gravity just changes nothing. Nothing changes when you change the gravity. It's like spring doesn't even care. The only thing it changes is where equilibrium is, but it doesn't change how it behaves or how it works. Any of that.
So if we were to go to like space and do this, it'd be the same?
Yep. Yep.
You mean zero gravity?
Exactly the same. Yep. Yep. Now, to be fair, you would need to use different springs. These springs wouldn't work in space just because they're all the way coiled up. So if you stretch them out, they would just like stop. So you would need things that are more like shock absorbers, like springs that are already spread out, so that you can compress them and expand them that way. So you'd have to have different springs to do it, but yes, they would work in space the same way they would on Earth. Yep. All right, any questions on the front about restoring force and the effects on period? We've talked about this a little bit, but I just want to make sure that we're clear on it before we go to the back. Okay, let's jump to the back. One thing here, and then we will do an example, and then we'll give you time to start on the practice. Then we'll do another example, and then you can finish it up. All right, for the pendulum lab, we talked about how speed and acceleration change during an oscillation. Do those properties behave similarly or differently for springs? So on the pendulum, we said it was like this. If you find it helpful. And then for a spring, it would be more like this. So this would be position 1, kind of at the maximum. So this is 1, going this way. 1, 2, 3, 4, 5. So this is the spring compressed. Then the spring stretches out a little bit. This, by the way, is equilibrium. Okay, spring gets to equilibrium. Okay, keeps going a little bit further. Stretch. Now it's starting to stretch out, and then it gets all the way stretched out as much as it can, and then it'll go back again. So it's going this way in its motion. And again, we got our spots 1, 2, 3, 4, 5. So when we did the pendulum lab, we said at positions 1, the velocity was 0 because it was at its maximum displacement. It wasn't going forward yet, but it wasn't going back anymore. As it went towards equilibrium, it increased its velocity. When it got to equilibrium, it was the fastest it could go. As it went away from equilibrium, it slowed down because gravity was pulling against it. And then at 5, on the other side, it was 0 because it wasn't going forward anymore, but it hadn't started coming back yet. That's what we said for pendulums. Turns out, it's the same for springs. Okay, let's look at the problem here.